So let's consider a 2 by 2 matrix. We'll keep it nice and simple. We'll look at 1, 2, 2, 1. And suppose that we want to multiply by this matrix repeatedly. We'll talk later on about why you might want to do such a thing and why it makes good sense to do that. But let's look at it geometrically. So let's also look at its action on the standard basis. If we look at A times 1, 0, we're just going to get the first column, 1, 2. And if we look at A times 0, 1, the other standard unit basis vector, we're going to get the second column, 2, 1. So if we graph what this looks like, say in terms of the good old unit square, so actually let me draw it a little smaller. Here we go. Okay, so here's our unit square, and we're going to start with, say, the first unit basis vector right here across the bottom. Oh wow, that went all thin. There we go. Okay, across the bottom. And then that gets mapped to 1, 2. So that would be this vector right here. Okay. Meanwhile, if we looked at the other unit basis vector 0, 1, so that's this one, then that guy gets mapped to 2, 1, so that's out here. Okay, and then the unit square is going to get transformed into this parallelogram, something like that. Okay, so now suppose somebody comes along with another vector, and let's go with the 4 minus 2. And they say, okay, what is A times U? And so you might be able to figure out kind of what that looks like by saying, okay, so out here 1, 3, 4, and then up 2. So what's going to happen to, oh, sorry, minus 2. So down here somewhere. So U looks like down here. What happens when we multiply by A? And so you might have some guess about what happens, but if somebody says, what if I multiply by A repeatedly? What if I multiply by A 8 times? Well, then you have no idea. What if I want to just keep on multiplying by A n times? Well, then it's even more confusing. However, instead of looking at the action on the standard basis, let's look at a different basis. So now, remember, for a basis, we're talking about R2, which is two-dimensional. So we just need a set of 2 linearly independent vectors. So in dimension 2, that means that they're not both on the same line. So I will take V1 to be 1, 1, and V2 to be minus 1, 1. Okay, so now let's take the same picture that we had before, but these guys aren't going to be there anymore. Okay. Oh, actually, you know what? Forget this part. We don't actually even want those. Ah, it's gone. Okay. What we want is we want this basis vector here, so that's going to be our V1, and then our V2 is going to be this one right here. Okay, so that's V2, and that's V1. Okay, so now let's look at what happens. So if we do the matrix product of A against 1, 1, we get 3, 3. And this is 3 times the very same vector that we started with. And let's also look at A times the other basis vector v2. When we do that multiplication, we find that we get 1 minus 1, which is -1 times the vector that we started with. So in each one of these cases, we did A times the vector, and we got a scalar multiple times the vector. So lambda here is a scalar. Okay, why do we use lambda? I don't know, tradition or something like that. So what's the upshot of this? Well, when you multiply by a given matrix, vectors move all over the place, and in general, they no longer point the same direction that they were pointing in the beginning. However, for these two particular vectors, so 1, 1 and minus 1, 1, they end up pointing along the same direction as they did before. And it looks a little bit like I'm lying because of the sign change, but let me just show you what I mean. So going back over here to this, let me finish drawing this picture here. So the image of v11 after the multiplication is going to be 3 times v11. So it points in the same direction, it just goes further out. So this one here is a times v1. And the image of v2 is going to be out here. So this is a v2. So it's on the same line. So it points in the same direction, or it's parallel to v2 in the fact that it's a scalar multiple of v2. It just happens to be a scalar multiple, which is a negative scalar. Okay. So maybe a better way to phrase this is that multiplication by a, it sends the span of v1 to the span of v1. So that vector space, any green vector, and so that includes, in fact, vectors that are down here on the vector space. Any green vector that gets multiplied by a is going to be a green vector again. It's going to land back on that same line. And any orange vector, so any point that I pick, if I take something that's somewhere anywhere on the orange line and I multiply by a, it's going to end up back on the orange line again. So that's the idea that we're looking for. So A acts very simply on this basis. So A of v1 is 3v1, and A of v2 is minus 1 times v2. So usually matrix multiplication is complicated, but if you pick the right vectors, then it turns out to be the same as scalar multiplication. So let's go back to the question about u. What to do with u, so to speak. So I can write u in terms of this basis. That's the whole point in having a basis. We can write vectors in terms of it. And so I can, how do I write that in terms of the basis? Well, let's see. What do I need to do? I need to solve the equation that looks like v1, v2, and I want to take some linear combination of those with some scalars. C1, C2, and I want to end up with this U that I've been given. So that means I'm going to take V1, V2, and I'm going to adjoin U, and I'm going to row reduce. And when I row reduce, I end up finding 1, 0, 0, 1, and 1 minus 3. Now, you better get the identity here, because V1 and V2 are supposed to form a basis. So you get the identity there if and only if your V1 and V2 is a basis, right? All right. So coming back to our equation for U, we have 1 copy of 1, 1, and minus 3 copies of minus 1, 1. And that gives us 4 minus 2. So you can let me just check the addition there. So I've got 1 plus negative 3 is 4, good. And on the bottom, 1 minus 3 is negative 2, good. Okay, so that checks out. All right, now we can take a look at the action of A when we multiply it against U. And we can even do it n times right off the bat, because this is going to be an times 1 copy of V1 minus 3 copies of V2, like we just found on the previous step here. And this is going to be, I can distribute the A's across, so I have an V1 minus 3 an V2, so I just pulled the 3 out in front. And now, because of this special magic vectors that we've chosen, an V1 is, well, each time you multiply V1 by A, you pop out a 3. You get a scalar multiple by 3. So it becomes 3 to the n V1 minus 3 times negative 1 to the n V2. And so that's, I'm using this property right here in order to do this step right here. And so now let's see, so this is 3n, 3n, doing the scalar multiplication back inside V1. Remember, V1 was the vector 1, 1. And I have minus 3 times, and then I've got negative minus 1 to the n and minus 1 to the n for V2. And so this is going to be 3 to the n plus 3 negative 1 to the n. And this is going to be 3 to the n minus 3 negative 1 to the n. And so you could write that down very easily for any n that you choose. Not only that, but geometrically you can now see what's going on very well back up in this picture over here, because we can see that if you take a vector now, what happens whenever you do a multiplication, what's happening? Well, the orange points are getting interchanged. They're reflecting across the green axis. And simultaneously, you're getting stretched in the direction of the green axis by a factor of 3. So that tells us that if we pick some point, so where was U to begin with? U was out here somewhere. Oh, we just found coordinates for it. So it's going to be, let's see, so it's got coordinates 1 and minus 3. So we go 1 in the direction of V1, and then minus 3 in the direction of V2. So we're out here. So this one right here is supposedly, what was it, 4 minus 2? Yeah, that looks reasonable. Okay, so here's U. Here you are. And when we multiply by A, what's going to happen is it's going to get stretched by a factor of 3 and reflected and end up over here somewhere. and so on and so forth. So points are going to go ping pong, ping pong, ping pong, back and forth around the green axis, heading that way each time you multiply by a.